a great honor of mine to have a talk devoted to parity theory. Will tell us about parity theory for links. So let's roll.
Thank you very much. Thanks very much, Vasily, for inviting me to speak here. I really appreciate it. And yeah, I'm going to talk about some extensions of parity to links. And it's a pleasure to give this talk, as some of the most expert people in the world on parity are in this call. So it's hopefully there should be some nice questions and some nice insight. So I'm going to share my screen.
Okay, you have a co-host now.
So we should be good to go. Excellent. So I'm going to mostly talk about the construction called the two-color parity, and describe some results about this. And along the way, I hope to be able to flag up some general principles that, in my thinking about parities for links, have come up. And I'd like to sort of advertise the problem of coming up with more and more parities for virtual links.
There was a book, Parity and Patterns in Low-Dimensional Topology. So I don't know whether you are aware of that. So by Denise Lyutka, Igor Nikonov, and myself, we are all here. So there was a book, and we were generalizing parity in many directions. It was something 5 years ago.
Yeah, and I hope to add a little bit to that. And also in the audience today are Luke Kaufman and Scott Baldridge, who just gave the previous two talks in this seminar on our joint work about graphenes. And of course, everything that I say today is all about virtual links, but in light of the previous two excellent talks, where they outlined the bijection between virtual links and these new graph theoretic objects called graphenes, the nice thing to note is that everything that we talk about with parities for virtual links is automatically carried over to parities for these graphene objects. So this is a nice interaction between what I'm going to say today and their talks. So I'm going to go quite fast and loose here, but the thing I want to say is that parity is an extremely powerful tool in the study of virtual knots. And parity is, the concept is of course due to our host today, Vasily Manturov, and then it's later developed and extended by many people, including people in the audience today, Nikonov, Lyutko, and many more.
Well, I would even say that maybe the first mention of parity was due to Luke Kaufman when he was talking about something like even right.
Yes, that's a great point. Yeah. So this is if I remember correctly, I think you're referring to the paper called self-indexing. No. Maybe I can't remember the title of that.
Self-linking invariant.
Yes. Thank you. Yes, that's the one. So a self-linking invariant of virtual knots, where Kaufman defines the odd rive. And so why is it so extremely powerful? Well, a few things, many very difficult results that are slippery and very hard to get your hands on without parity become miraculously extremely easy to prove when you have the parity construction. And I'll just give one example. There's a very nice sort of general principle is that parity allows you to say, for example, so e.g., you can prove that a checkerboard, so I'll just call this CB, a checkerboard colorable knot, virtual knot, has a minimal genus checkerboard colorable diagram. And by minimal genus here, I mean it's the genus of the supporting surface, the genus of its Carter surface, as it's also known, is the smallest possible in the virtual knot class. And this, if you try to do this without parity, this is really slippery and very difficult to get the two notions of checkerboard colorability and minimal genus to play nicely. But with parity, it becomes much easier to see results like this. And I think this is the prototypical example of how powerful parity is, that it lets you really pin down notions that would otherwise be hard to combine. And I want to stress that this isn't the case of virtual knots. And it's, how much space has this page got? Okay. And it's an important problem to prove or extend parities to virtual links, because, as I hope I've given you a tiny flavor of, parity is extremely useful when studying virtual knots, and one would dearly love to be able to extend that power to virtual links. And there have been a few. There's one that you can do almost immediately, and this is I refer to this as the naive parity, but other people might have different names for it. And you could simply declare self-crossings as even and mixed crossings as odd, by which I mean crossings between the same link component as even, and then crossings between two distinct link components as odd. This satisfies the axioms of a parity, but it doesn't enjoy much of the power that you would really want from a parity theory for links. Another extension, or a couple of extensions are due to Im and Park, and there's a slightly more recent one due to Zhu, and there's more. But a number of these extensions suffer from the following defect. So they are unable to distinguish mixed crossings between the same components rather. And what do I mean by this? I mean that if we have a link diagram, D, which is made up of D1 through to Dn, then these parities, these parities do the following. So if we have such a link, then these extensions or these parities declare crossings between the ith component and the jth component as all odd or all even. So it means that if one crossing between these two components is odd, then they're all odd. And what this means is that invariants extracted are determined by the pairwise linking numbers. So as we mentioned, the paper a self-linking invariant of virtual knots by Kaufman, and that in which the odd withe is defined, and this is a sum of all the odd crossings of a link diagram shown to be a virtual link invariant, virtual knot invariant, sorry. So if you tried to play the same game with these parities here, it wouldn't give you an invariant it would give you an invariant that was almost entirely dependent on the pairwise linking numbers, which is not, again, not so powerful. It's an upgrade from the naive parity in some cases, but it's not that much of an upgrade. And then as a third extension, Vasily has an extension to two component links that appear as cross sections of cobordisms. And the idea here is that if we have a cobordism between two virtual knots, then if we're starting at a virtual knot, we can apply a parity theory, and then we can look at the double point lines of this cobordism, and you can extend the parities of the crossings to the whole double point lines. And this is a nice idea, and I think it bears more study, actually.
Well, actually, this works in two cases very nicely. So if we know that the genus of the cobordism is 0, or if we know that it's checkerboard colorable, then everything can be extended. But in general case, it seems to be unknown. And on the other hand, we have a problem we still would be very happy to know something about, is how to do something like parity bracket for two-dimensional knots.
Right. Yeah, I think. Well, maybe when I've said a few things about the two-color parity, I can present an idea I had towards that end. And then, yeah, so these are some extensions of parity to links, but perhaps one might say that a candidate parity to links hasn't really been found that captures lots of the power of parity for knots in a wide class of applicability. And so the two-color parity by this guy R dot is an extension, or rather it is a parity for a large class of virtual links. It doesn't require any concordance information as the previous example. And it in particular can distinguish mixed crossings between the same components as we saw before. So the parities, including those developed by Im and Park and Zhu, as I mentioned, they were unable to distinguish mixed crossings between fixed components. This parity that I'll outline today is able to do so. And it's also has a very nice feature. It's the extension of the Gaussian parity. And the Gaussian parity is perhaps the most well-known parity for knots and one of the most powerful. This is as defined by Kaufman in his self-linking invariant paper. And this two-color parity really does naturally extend the Gaussian parity to a very large class of links. Now, before giving the definition and proving some things about it and showing you some things, I want to highlight something that is needed in the construction of the two-color parity that I think is prototypical for the whole problem of extending parities to links. And that is that the more I try to come up with parities for links, the more I find that one needs to make an additional choice, in the sense that there is, for virtual knots, it turns out that there's only one choice of some object. But then when you pass to virtual links, you have to make a choice, and this yields a parity. So this is sort of governed in the two coloring case by, I won't tell you what the two coloring is yet, but I'll just say that a two coloring, it's a particular coloring of a virtual diagram. And not all diagrams possess such a coloring, but many do. And the idea behind the two-color parity is as follows. If I pick a two coloring of a knot or a link diagram, then I pick an orientation, these two choices naturally define for me a parity theory. So we can think of these things as being related, sort of vertices of this triangle, and fixing any two vertices uniquely defines the third. So I resolve this by working with oriented links. So my objects of study are always oriented virtual links. And then when I pick a two coloring, I obtain a parity theory, and I'm able to achieve many of the things one can do in the knot case, in the link case. And to fully flesh this idea out, in the case of a knot, I don't know if you can see, but when I change color, my drawing application doesn't let me scroll, which is acutely annoying. So for knots, it turns out, as I'll show you in a second, for knots, there is only one two coloring up to dualization, but really there's only one. And of course, up to reversal, there's only one orientation. So this uniquely, so with this triangle that I've outlined here, this defines a unique parity, and this turns out to be the Gaussian parity. So if I hand this scheme a knot and pick the only possible two coloring and the only possible orientation, this yields a parity, and it turns out to be the Gaussian parity. And the framework I'm going to describe allows you to generalize this to links. And so this justifies the notion, or justifies the claim rather, that the parity thus defined really is the extension of the Gaussian parity to links of more than one component. Of course, to a certain class, we can't extend them to all virtual links, but we can to a large class of them. So I hope, just to postpone the definition a little bit further, I think that extending parities to links fits into this general framework where instead of having a two coloring, one might need to pick some other auxiliary object. And you'd get a new triangle with some mysterious auxiliary object, a parity, an orientation, and fixing any two vertices should give you the third. And in this construction, in the two coloring construction, this object here is combinatorial. It's a two coloring, as I'll show you in a second. But it would be extremely interesting to find topological auxiliary objects. One could look at all the different ways that virtual knots are represented topologically and try to, virtual links rather, are represented topologically and attempt to pick an auxiliary object here.
Well, you know, more or less, the idea of trisecants, horizontal trisecants and group G and K appeared from the following point of view. Classical braids do have a sort of, whenever we have some homology of the underlying space, we do have parity. And for complements of knots and links, we certainly have some homology. And for braids, this homology is quite visible. So this means that we should tackle knots from another point of view. So for trisecants, we can find something like indices. And so I suggest to try to classify parity for, say, what we did with braids. But then from braids, we can go to links. Well, anyway, whenever we have homology, so when we try to tackle parity just for classical knots, we do not succeed just because we have no homology for the R2, but other configuration spaces for more points, they are much more powerful. They have more homology, so this homology should give rise to parity.
Yeah, that's a great point, and so that's showing that in just to add to that viewpoint, in many ways, virtual knots behave like classical links. For example, not all virtual knots possess a Seifert surface. Not all links possess a Seifert surface where each component bounds a disjoint. A Seifert surface for a link, you'd really want it to be a collection of disjoint surfaces, each bounding an individual link component. Not all links possess such a thing. So there's many relationships where classical links appear to behave very similarly to virtual knots. And so to add to Vasily's point, perhaps trying to find parities for links by finding new objects to place as this third vertex could also inform on finding non-trivial parities for classical knots, which is a very interesting problem as well. So I want to give you the banner headlines of the two-color parity and what it can do before giving you an overview of how it's defined. Because I think it's a number of its features are very useful, and certainly they show that the two-color parity is stronger and more useful than some of the previous extensions of parities to links. So this allows us to define the two-color writhe of an oriented link, which, postponing the definition for a couple of seconds, this is essentially you just take all possible two colorings and you do the odd-rive construction for every single two coloring, and then you package them all up into a vector. But I'll give you the precise definition in a second, but suffice it to say, what does the two color ith do? It extends, my cuckoo clock is really going for it. There it goes. Extends the odd-rive to links, or to two colorable links. It's a concordance invariant as well, which is, I think, maybe my favorite property of it. The odd-rive is a concordance invariant for virtual knots, so it's more evidence that this construction is really the proper generalization of the Gaussian parity, because this invariant of virtual links yields a concordance invariant of virtual links. So in particular, it obstructs the strong sliceness of virtual links. It obstructs amphicchirality and checkerboard colorability. And because it's a concordance invariant, it does these things within a concordance class. So it can be used to prove that your knot is not concordant to an amphichiral knot, or not concordant, sorry, link. Your link is not concordant to an amphichiral link or to a checkerboard colorable link, for example. I'll show you an example of that shortly.
Excuse me, by the way, my invariant for cobordisms, I mean, the one I called L in 2012, which I first defined via some dihedral group, actually can be treated as follows. So having parity, we can define signs for odd crossings. And in fact, besides just those signs which come from local right numbers, even for free knots, we do have some additional sign. And this, so if we count odd crossings with signs, we get yet another concordance invariance. So I wonder whether you can do the same for links for two colors. So just look at my L invariant and try to do it for two colors, whether you can get signs.
Yeah, I think that's really interesting. And related to free knots, this parity actually descends to a parity on free links. And it's strictly stronger than the naive parity, which is what you'd hope. But it's also strictly stronger than the imparc parity. So the invariance you pull out of the imparc parity and the naive parity, the two color ith is strictly stronger than them. And in fact, there are many examples of links undetected by these invariants that are detected by the two color ith, for example. And finally, the application I'd like to finish with is that it allows you to prove that a checkerboard colorable link has a checkerboard colorable minimal genus diagram. And this is in line with what I was mentioning at the beginning, that this is maybe the best, in my mind, one of the most useful things that Parity allows you to do is it allows you to marry often disparate concepts in virtual knot theory and show that, and work simultaneously with perhaps disparate concepts And here, checkerboard colorability and minimal genus don't necessarily play very nicely. And this is an instance where this parity theory for links lets you prove that if your link is checkerboard colorable, then you can find a minimal genus diagram of it that is checkerboard colorable. And this is really useful for proofs of other things. So it's sort of like one of those wish theorems that lets you say, well, say if you're working with checkerboard colorable things in the wild for some other reason, and then you came across a part in your proof where you wanted to be able to invoke minimal genus of your virtual link. Without this theorem here, that's a priori not true. You might not, even if your link is minimal, it's checkerboard colorable, sorry, you might not be able to find a checkerboard colorable minimal genus diagram. And so these types of theorems are really useful for proving other things about checkerboard colorable links. Okay, so that's a smattering of things you can do with the two-color parity. And for the remainder of my time, I'd like to sketch the definition and the construction. So here's the definition of the two-color parity. A two-coloring, maybe I'll just call it two-color for now, is the coloring of a virtual link diagram of the following form. As always in seminars, often a picture is worth many, many words. So first I'll give you the picture. Say if I had this virtual link, we might call it the virtual whitehead link or something like that. Then a two coloring of it is as follows. I color its arcs exactly one of two colors. I'm gonna sorry, technical difficulties. So I color its arcs exactly one of two colors, red or green, such that I change color when I go through a classical crossing. And I'll put the green in a second. And I do this for every component. And when I go through a virtual crossing, I ignore it. The color stays the same.
Well, you know, there was a joint paper we wrote with Denise Lyutko about some polynomials and biquandles which dominate parity on one hand and Sam Nelson's constructions on the other hand. So in some sense, this is just the simplest biquandle, this coloring. And
yeah.
So we can look at biquandles. So you can generalize many things like parities and maybe your invariance as well.
Yeah, that's a good point. So the reason why this was introduced, or this first appears in Kaufman's self-linking invariant paper. And it's where it's known as a proper coloring. And I hope you'll forgive me the terminologically inflationary practice of giving something that already had a name a new name. But I call it a two coloring because, as Vasily just mentioned, you could actually do this exact same construction with as many colors as you like. So you could, there's 3 colorings, 4 colorings, 5 colorings. The set of links that possess a 3 coloring is smaller than the set that possesses a 2 coloring, for example. So as you increase the numbers of colors you use, you do reduce the virtual links that you're allowed to consider. However, your invariants do get potentially stronger as you increase the number of colors. But I'm just going to talk about two colorings today. So you take such an object, and it's a nice little combinatorial exercise to prove that that a V-link has a two coloring if and only if the following is true. So I should have given my two link a name, sorry. I'll call my two link L, and it has components L1 up to Ln. If and only if the linking number between Li and the rest of the diagram is even for all I. So if it just has even pairwise linking number with all other components, and so, sorry, no, I've said that wrong. If it has even pairwise linking number with the rest of the diagram, and this is actually a key point, this does not imply that the pairwise linking numbers between two individual components are even. And this is what actually, that observation is what down the line gives you that the parity that we construct like this is stronger than the in-park parity, for example. And this is what allows it to distinguish links of more than one component. Maybe I'll put it there. So that's a nice exercise to prove this, that a two coloring is possessed if and only if these linking numbers are all even. And then it's also an observation that follows quickly from this, that if a virtual link possesses or is two colorable, let's say, then, again, I forgot to give it a name. For two colorable link L, then it has 2 to the number of components, two colorings. Because if you give me a 1-2 coloring of it, then I can produce all the others required to make up this 2 to the number of components just by flipping the coloring on one component. So the link we saw above here, this should have 4 2 colorings, and they are found from this one simply by, I could hold the coloring constant on the figure of 8 components and then shunt red along to green and green along to red on the central one, and so on and so forth. And doing that flip will give me all the colorings I want. And so this is to show that not all virtual links possess such a 2 coloring. Of course, the virtual knot theorists, maybe the virtual knot theorists' famous non-example for many, many things is the virtual hop link. This fails many, many things that you expect a link to satisfy, and this is a very simple non-2 colorable link. But I want to show you that maybe it's not as obvious as you think, because say the Gauss diagram rather of the virtual hop link looks like this. When I don't mind what the orientation or sign of this chord is. But because I only need the linking numbers with the rest of the diagram to be even, not individual pairwise linking numbers, I could create a 2 colorable link like this. So this kind of looks like a virtual Borromean rings. It's like it's the Gauss diagram of this, where you put real crossings however you like in there. So notice that the pairwise linking numbers between these two components are odd, which can't happen classically. So this is a virtual phenomenon, but nevertheless, this link is still two colorable, which is a useful thing. So this is two colorable. So now I can define the two color parity as follows. Let L, or no, D be an oriented virtual link diagram.
Excuse me, here I have a comment. The comment is more or less as follows. So if we have some configuration spaces like classical link, like something for classical links, and we try to draw something on the plane or in just R3, then many things turn out to be even just because of the absence of homologic groups for R2 or R3. But sometimes it happens that we have something like A to the -1, B to the -1, which are quite similar to this Borromean ring, and which actually appear in link homotopy theory. And in fact, this is one of the sources of parity in the classical link case. Okay.
Yeah, so I think there are lots of parallels between parities for classical things and parities for virtual links. I do think there's some strong parallels there. So you take an oriented virtual link diagram and then define an oriented virtual link diagram and see a two coloring of it. So this goes to the triangle I was showing you a few minutes ago, where I have to pick an orientation. So I'm working with virtual link diagrams, and then I have to pick a two coloring of it. It's not enough for it just to be two colorable. I have to pick one. Define the function P, which depends on this two coloring, as it's going to be a parity, so it's a function on the classical crossings, like so. If I have a crossing that looks like this, we declare that to be even, so that gets mapped to 0. And if I have a crossing that looks like this, I define that to be odd. And of course, these are...
That's exactly what we did in our paper with Denise.
Pardon?
So that's exactly what we did in our paper with Denise when we generalized SAM's construction.
Okay, so this is also up to our rotation, of course. I could also have red on the right and green on the left, and red on the top and green on the bottom. I just mean up to rotation. So this is showing that I need the two coloring and the orientation here. If I wasn't working with oriented links, then I can't tell these two configurations apart up to rotation. So the orientation sort of breaks the symmetry and allows me to distinguish these two things. So that's, we really do, or at least at this stage, it appears to me that the picking an orientation and picking a two coloring are really required. Okay, and so proposition is that this, or the function PC is a parity. And so perhaps I will give well, I'm a little bit pressed for time, so I'll give the diagrammatic, the quick diagrammatic way of saying the parity axioms. So here I have a function on the crossings, and if it's going to be a parity, then the parities of all crossings involved in a Reidemeister move must sum to 0 in Z mod 2 for it to be a strong parity. But perhaps I'll just say that if I see a Reidemeister move like this, this has to be even. If I see a Reidemeister 2, then they both have to get the same parity. I can't have one odd and one even. And finally, the third Reidemeister move. What's the succinct way to write this? Because for a strong parity, you can just say that the crossing parities have to sum to 0, but the two color parity is not actually a strong parity. Essentially, I'll just say it in words. What you want is either all the crossings involved are even, or two crossings involved are even, or all of them are even. Sorry, hang on, I've said that wrong. Either all the crossings are even, two crossings are odd, or all of them are odd. Those are the only three possibilities in a Reidemeister 3 move. So maybe I'll just write in words. No, cannot have exactly one odd crossing. We rule that out. And many people in this seminar have seen, are very, very familiar with the parity axioms. But if you're not so familiar, the way I view the parity axioms is as simply defined so that parity projection works. And what I mean by that is, if I have a Reidemeister move between two diagrams, and then I converted all of the odd crossings to virtual crossings and just deleted them by virtualizing them, the parity axioms guarantee that after I convert everything to all the odd crossings to virtual ones, I can still do that Reidemeister move. So if we look here, for example, on the R2, if both of them are even, then of course nothing changes, I can still do the move. If both of them are odd, then this just turns into a virtual Reidemeister 2, and I can still do it. And I've defined away the possibility that one is odd and one is even, in which case after projection I couldn't do this move. So that's sort of why in my mind, the parity axioms are so useful. They let you project and still do sequences of Reidemeister moves. And so for today, I'm probably not going to, the proof of this is simply case-by-case checking in any case, but let's just do one case just to outline what we do. Well, we just look at we look at all possible situations. No, I don't need an arrow here, sorry. I look here and I notice that if the configuration is like this, then they're both odd. And the only other possible configuration is like this. In which case they're both even. And so you can quite quickly make the combinatorial check and verify that this is a parity. And the key thing I want to also stress is that this is completely local to the crossing. And this is one of the reasons I really like this construction, and one of the reasons I think it has lots of applicability, is that we don't have to know the rest of the link diagram. Specifically, if you just give me a crossing and it's oriented, for example, and then I know that, say, the two coloring configuration at that crossing, I can tell you just by looking purely locally at the crossing whether it's even or odd. I don't care whether this is a self crossing between a component and itself, or a mixed crossing between two distinct components. It makes no difference for this parity definition, and that's a feature that is not shared by the other extensions of parity to links. They very fundamentally separate crossings into mixed and self, and they have a different way to compute the parity depending on whether the crossing is a self crossing or a mixed crossing. And this is a benefit of the two color parity, that I don't need to know that. I just compute it completely locally at a crossing. So maybe I'll write some words at this definition. Local in nature. Okay, so that yields a parity. And in the final 5 minutes, perhaps I'll just...
No, these are not final 5 minutes. Usually we have an hour and a half. So you are free to take as much as possible.
Okay, well, maybe I won't take the full 90 minutes, but maybe I'll keep going. Yeah, so I'll keep going for longer than 5, certainly. Okay. So this definition is local. It yields a parity. So it yields a parity theory for the large class of two colorable virtual links. And as I outlined earlier, that it has a number of applications. And perhaps maybe the one I'll say is the concordance invariance then, because I think this is maybe my personal favorite. And so this allows us to do the following. Before I make this definition, I'll point out 2 things. So note, if C and C prime are 2 distinct two colorings of the diagram D, and C is a self-crossing, then the parity with respect to one of the colorings of C is the same with respect to the other parity. So by that I mean, I told you that this whole construction was very dependent on picking a 2 coloring, and it is in general. Different 2 colorings will give you different parities, but for self crossings, that doesn't happen. And so maybe I'll give a quick diagram as to why. If I have a self-crossing between links, then say it looks like this, for example. Then, and say this is in the coloring C. Well, how could I get to a coloring C prime? All I would be doing would be, I would be flipping the coloring on some subset of the components of D. So I'd be converting red to green and green to red on some components. So say if I'm to go from C to C prime, I actually have to flip the coloring on this particular component that we're seeing in the crossing. Well, all that would do would be to move, because this is a self-crossing, this green would become a red, this green would become a red, and the same as happens on the top. And so as you can see, this crossing is odd with this coloring, and it's certainly odd with this coloring too, because the component involved is having its coloring flipped on all of it. So this means that self crossings it doesn't matter which coloring you pick, they have the same parity. And mixed crossings do though. Mixed crossings will change their parity if you flip. And the final thing to note is that we saw that L, so a diagram D of a virtual link L has 2 to the number of link components of L 2 colorings. But it turns out for our applications, we only need half of them. Why is that? Because if C, or C prime, is obtained, so this is a 2 coloring, obtained from C by flipping the coloring on every component, then the parity with respect to C prime of every crossing is equal to the parity with respect to C, and this is for all crossings, not just self crossings, it's for everything. So this means that although we have 2 to the number of components of the colorings, we should really only need to keep track of half of these, because if I flip up all of the colors, it doesn't change the parity. And perhaps I'll have a quick example of that to really concretize the situation. If I have this 2 coloring here of the link we saw a few minutes ago, and then I can also have this 2 coloring, then let's orient this. Let's say it looks like this. So here, this crossing is even. When I flipped all the colors, this crossing is also even. And that's an if and only if. And this works for even crossing, self crossings and mixed crossings. So what this means is I should only really keep track of half. If I want to, when I'm extracting invariants, I can make my life easier like that. And so I come up with a terminology to capture this. So a generating set of 2 colorings for a diagram D is a set S of cardinality equal to half the number of 2 colorings, 2 to the number of components minus 1, such that if C is a 2 coloring of D, then either C is in this set, or C bar is in this set, where C bar is obtained from C by sending red to green and green to red. So just doing this process here. So for example, this would be C, and then this would be C bar in this case. So I change red to green globally everywhere, and that gives me C bar. So this is just a little bit of terminology that allows me to divide by half as I know I can, and compute on this set of 2 colorings. So we can now define the 2 color writhe. So let D be a diagram of the virtual link or the oriented virtual link L, and S, a generating set of two colorings of D, denote by J of C of the diagram D, the sum of the odd, or rather sum over C, a crossing of D, such that it is odd with respect to this particular two coloring, this particular parity, just the sign of C. So this, I'm taking exactly the odd writhe of this diagram, but with respect to this choice of two coloring. Because remember, to define the parity, I had to pick two coloring. But this diagram, so this should be 4C in my generating, 4C in my generating set. So I just take the odd writhe as we might normally do, but this is a link, so it has many possible two colorings, and they all give a priori different parities for crossings. So I package that all up into a big long vector. So now I denote by J2 of D, the multiset.
Well, you know, as for multisets, it's very good because, well, for just usual for usual double crossings, in fact, whatever parity two crossings have, they may be pulled to each other to take part in a third Reidemeister mode. But in higher dimensional theory, crossings may have many parities, many different parities, and if they are very much distinct, then they cannot take part in a move. So in some sense, we have some truly non-commutative things. We have truly non-commutative things, and so I suggest you to look at and to compare what we have here with indices for G and 3 and other things, because, well, if we have multi-component parity, it may be very interesting from the point of view whether two crossings can take part in a Reidemeister tree. In fact,
yes, no, that's really interesting. Yeah, okay, I see what you mean, actually. Yeah. Yeah, so you can either think about this as being a set where every crossing gets, you pick a crossing, you pick a two coloring, that gives you a parity. Or, as Vasily was just alluding to, you could think about it a different way, and you could say, you just take a crossing of the link diagram, and instead of parity being a Z mod 2 valued thing, you could think about it as being, a Z mod 2 cross, you could think about it being valued in Z mod 2 across itself n times, and a vector. And maybe there's some nice parity axioms for such a thing. Yeah, that's a great point. But in this case, the word multiset is just used because some of these quantities might be the same. And so I just have to be careful with that notation. And this is known as the two color writhe of the diagram D. And no prizes for guessing, this is a link invariant, virtual link invariant. is an invariant of oriented to colorable virtual links. And I'm probably not going to prove that, but it's quite a straightforward combinatorial exercise, and it's a consequence of the parity axioms actually that this is.
Well, I think as for those which are not too colorable, you can create something like too colorable cover, and then more or less you can put dots, or you can switch between colors by some transposition. So I think it's not a great deal to define two colorability for those which are not too colorable.
Yeah, yeah, you could do that using cut points. That's a good point. And so this invariant has all of the applications that I said a few minutes ago. But before I tell you about concordance invariants, perhaps I'll just say for the parity experts, a very strange thing happens when you project with respect to this parity. It is not closed under parity projection. So maybe I'll say this as a warning. There exists a two colorable link L such that parity projection yields some link P of L that is not two colorable. I was very surprised when my colleague Hans Boden said to me, well, you should be able to parity project as many times as you like. And so I tried to prove it, and then I was actually on an aeroplane when I found the diagram of this link that doesn't, that you parity project and you actually now fail to be two colorable. So this is quite interesting, and I haven't really explored this very much, but it means that you, unlike many other parities where you can just project and project and project as many times as you like and you sort of limit to something, in this case, that can completely fail, and you can project some number of times and then you now have to stop and you can't project anymore. So that's something important to flag up for those who have spent a lot of time thinking about parity projection. And so, yeah, so I'll finish today by sort of justifying the proposition that let L and L prime be concordant virtual links. And here I mean concordant in the strong sense that each link component must bound its own cylinder. So maybe I'll just say this in brackets, that there exists a disjoint union of annuli embedded in some four manifold such that the boundary of this disjoint union of annuli is the disjoint union of the links, and I, or rather there's one annulus for every link component. I don't want to see something like two components going into one. I want, so this is bad. I want some nice annuli that are allowed to link in the full manifold. So let L and L prime be concordant, then the two coloride of L is equal to the two coloride of L prime. And this extends the result in the not case that the odd rive is a concordance invariant. And maybe when I first saw that result, I was very surprised. I didn't think this extremely simply defined invariant, like the odd rive, could possibly be concordant invariant, some sort of, interacting nicely with four-dimensional transformations. But it's actually a really deep consequence of something about parity that odd crossings with respect to a parity can only be created in pairs, and they can only be destroyed in pairs. They're like a particle and its antiparticle. And this phenomenon, this cancellation property, is preserved even if you allow another dimension of evolution. It turns out if you have two odd crossings in a link diagram, and then you allow that link diagram to evolve in time, i.e. a concordance, you still can only cancel these things in pairs. It doesn't give you a new way of cancelling, essentially. And this actually goes back to the diagram I drew for Silly's extension of link parity, where we had entire double point lines of a cobordism. That's kind of also what's going on there. And so perhaps in 5 minutes, I'll just briefly outline why this is the case. It is a shameless self-promotion because maybe you could prove this another way, but I prove it by using a homology theory that I introduced. So for oriented virtual links L, there exists a bigraded, finitely generated abelian group DKHL, known as the doubled Kovanov homology. And this is functorial with respect to link concordance, and there's still a lot of things that I don't know about this invariant that I'd like to know. But one of the things that I can tell you is that, so I told you this was bigraded, and so it has two gradings, I and J. And this I grading is called the homological grading. And it turns out that the two coloride of this link L is equal to the homological degree, or the homological grading support of this homology group. So by this, I mean, this homology group is non-trivial in precisely the homological degrees equal to this, this multiset. So if an integer appears in this multiset, then this group has a non-trivial element of that grading, of that homological grading. And then you combine this result So this is the first observation to make. And the second observation is that this homological grading support, so all these numbers in which this group has non-trivial homological grading is concordance invariant. And that's something that's it's not extremely hard to prove, but it does require some work. But then comparing 1 and 2 allow you to conclude that this is a concordance invariant too. So this invariant here, the two-color ride is appearing as a important quantity in this much more sophisticated invariant here, and the concordance invariance of this descends to the concordance invariance of this. And this allows you, everything you can say about the two-color ride now extends across the entire concordance class of the link. So as I said at the beginning, it means you can obstruct checkerboard colorability in an entire concordance class. You can obstruct amphichirality. And of course, this means you can also, so maybe I'll finish with this corollary. It means you can also obstruct the sliceness of a link. So if corollary, if J to L is not equal to a set containing 0, then L is not strongly sliced. So L doesn't bound a nice disjoint collection of disks. And I think that there's more to extract from this relationship, which I'd like to do. But for today, I'd like to finish there, and thanks very much for your attention.
Yeah, that's great. Thank you very much. Just one question. So we have some signs for odd crossings. Maybe these signs can give us some further grading. Let's try to think about that. So we categorize
yes.
things. So let's categorize them as well. So we have the L invariant, and let's try to categorize it.
Yeah, that's a great point. Yeah, I didn't think of that. That's a good point.
Dear colleagues, please ask your questions. I have left some questions on the chat line. Please unmute your microphones and write on the chat line. So thanks, Will, for the great talk. So please ask your question. Are there any questions or comments? We'll just take a look at my questions.
Yeah, okay, so let's have a look. Yeah, so you mentioned about Legendrian links and having something like a crossing index. That's a good point. And I also think that kind of goes, that fits in nicely to my my sort of schematic with you know, something topological, combinatorial, some auxiliary choice, and a parity and an orientation, and you getting, if you pick enough vertices, you get the, if you pick 2 vertices, you get the third. And so if you think about Legendrian stuff, then that, you know, you're picking a contact structure. So that's a nice example of sort of this schematic.
Well, frankly speaking, parity is something coming from homology in the configuration space. Whenever we have a good structure, it is some manifold in the configuration space or something like that. So it should give rise to new homology classes and new parities, I think. So it has to be discussed. Okay, any further questions, remarks, comments? Well, if it's not the case, so let's thank the speaker again, and I'd like to announce what's going on soon. So next month,